About that. So this mini course will be about networks. So why do we care about networks and why are they so exciting? Well, basically because they're everywhere around us, and there are more and more networks around us. And the most interesting fact is that there's more and more data about networks, and in fact, lots and lots of data about networks. And that leads us to understand very interesting statistical inference problems about large networks. So that's what this basic course is going to be about. But here we're going to really focus on very basic models and basic questions, okay? And hopefully understand some basic techniques in how to handle these. Okay, so of course, if you want to understand real data, you're going to have to dig into the details and apply a sophisticated model and so on. But here we're going to really focus on understanding basic structures, basic models, basic techniques, okay? Yes, so this course is co-designed with Sebastian Bubeck, also from Microsoft Research. He unfortunately cannot be here, so this is all together with him. And I will have notes on my webpage. It should be easy to find from this link. There are already lecture notes for the first two lectures there, and I'll put up the remaining notes later this week. But I mean, my lectures won't exactly follow those notes, so those are meant more to read afterwards if you're interested in more things. So no need to read ahead of time. Okay, so let me jump right in. So we'll talk about networks. And there are all kinds of different networks. So if you look at Facebook is a massive network with over 1 billion people in it, and there's a lot of community structure in social networks in general. Just because you form communities with people you go to school with, people you work with, people you're in the same location with, and so on. There are many other types of networks, for instance, networks with geometric structure. So think about any type of network that comes from some kind of physical consideration, such as if you look at a country such as Brazil and you look at the road network between cities, this is something that really it has some underlying geometry of the country, and it has some kind of two-dimensional geometry. So these are such models, but there are all kinds of other networks where it's really some kind of feature space where the geometry is coming from. So we'll talk about these later. And so another important type of structure is networks that are evolving over time. So again, Facebook is not a static network. You have more and more users each day, and friendships are being made and broken as we speak. And there are all kinds of other structures you might be interested in. And basically, the type of structure you're interested in will influence the type of questions you ask, and that will really that's a major point I want to make, is that really the types of questions you want to ask should depend on the structure you want to uncover. Okay? So we'll be focusing on these three types of structures, but there are other structures you might be interested in. And today, I'll be talking about community structure. Then tomorrow and Wednesday, I'll talk about models and questions related to geometric structure. And in the last two lectures, I'll talk about time-evolving networks. Okay? So in particular, these two, and the first one are kind of independent, but there's lots of common underlying principles and general ideas, but they're largely independent. Okay, any questions so far? Okay, feel free to interrupt with any questions. It's best if this is very interactive. Okay. So let me jump straight into the first lecture about networks with community structure. So basically, finding underlying community structure is a very important problem, and there are many clustering algorithms. And the main question we're interested in is, well, how do they perform? Is one algorithm better than the other? How can we say something about this? So if we look at real data, then it's unclear how to distinguish one algorithm from the other, because oftentimes the underlying ground truth is not known. Moreover, sometimes there isn't even a real underlying ground truth, because it's, how to define a community is not something that is clear at all. So to do something about this, what we're going to consider are probabilistic generative models. So a probabilistic generative model is just some model of a random graph with some kind of community structure. And the nice thing about this is, so first of all, these can just serve as models of graphs with community structure. But the nice thing about this is that these can serve as a benchmark. To compare different algorithms. And why is this so? Because the ground truth is known. Okay, so that's the nice thing about probabilistic generative models. And the main question we'll be interested in is, what are the fundamental limits to any algorithm, any reconstruction algorithm? Or community dissection algorithm. Okay? Any questions about the basic setup? Okay, so I'll jump straight into the stochastic block model. Yes? Yes, so ground truth is, suppose I have some graph with n vertices. Those are, say, the people in your network, and you know that they have labels. So each one is assigned to one of the communities. And these are hidden but really known. So it's well defined which node belongs to which community. Yeah, that's what I mean by the ground truth is known. But let me define the stochastic block model, and then it should be very clear. So the stochastic block model is a model for community structure that was introduced over 30 years ago in the sociology literature. And it has been probably the most popular model to study in the social network literature. Okay, and the community detection literature. So what is the stochastic block model? So introduced by Holland et al. In '83. Okay, so there are several communities. And so there are edges between vertices within the different communities. And also between communities. And maybe some are very weakly connected, some are more densely connected, and so on. Okay? So the model is as follows. There are n vertices. There are k communities. So here k is 4, and in general we're going to consider k to be fixed, not changing with n. There's some probability vector p, p1 through pk, and this will give you the relative sizes of the communities. So now how do we define the model? So for every vertex, we pick a community according to this probability vector p. So that is, so the community of V will be denoted by sigma V, and so this is equal to I. So V belongs to the ith community with probability pi. Okay. Any questions? Yes. The bracket. Sorry, this bracket. So n just denotes 1, 2 through n. Sorry. Yeah. Yeah, feel free to interrupt with any kind of questions like this. So now, so I told you how I pick a community for each vertex, and what I have to define is still how do I put edges between vertices. So what I want is that the edge probability should depend on which communities these guys belong to. Do they belong to the same community, but a different community, or two different communities? So if I have two vertices uv, then I will connect them with an edge with some probability that depends on the labels, sigma u, sigma v. Hope you can see this. So there's a matrix Q, which is a k by k matrix, and this determines the connections between the vertices. Okay? Any questions? No, so this could be all ones, and then everyone is connected. Yeah. So, well, this is symmetric. That's the only thing we assume, but otherwise the entries can be anything between 0 and 1. Yeah. So this is denoted as the stochastic block model with parameters n, p, which is the relative sizes of the communities, and q, which determines the connection probabilities. Okay? And here in the notation, k, the number of communities k is kind of implicit, but that is the length of the vector p, and the size of the matrix q is k by k. So it's probably illustrative to keep a simple example in mind. So consider symmetric communities. So I have three communities of equal size, and they all look similar. Okay, so here the PIs are just 1 over k, so they all have the same size, and the within community probability is A, and the between community probability is B. And yeah, for I not equal to j. And say if you have more connections within a community than between communities, then A is greater than B. But you could have it the other way as well. Okay? Any questions? Yes? No, yeah. This is an important point. So this is how you define the model, but then what you're given is the graph without the labels. So that's known to, somebody. That's known to God, but not to us. Okay? Yeah, so what we're given, so yeah, the problem is we want to recover, the goal is recover the label sigma from the unlabeled realization of the graph. Does that make sense? Okay, any other questions? Okay, so this is our goal, but what does this exactly mean? Because there could be various notions of recovery. And indeed, there are actually many different notions of recovery that can be interesting. Because maybe you can recover everything, maybe you can just say that these guys are in the same community, probably, but I'm not quite sure. Okay, so let me tell you about the different notions of recovery. So the weakest notion, known as weak recovery, or detection, is that, so you have weak recovery if the algorithm outputs a partition of the vertices that is correlated with the true partition. Okay, so what do I mean by this? So suppose there are only two communities, they have equal size, and you're in this example with two communities. Then one thing I could do is for every vertex, I could just flip a coin to say that this vertex is from community 1 or community 2, and I'll be right for each vertex with probability half, so I get half of the vertices right. But can you get 51% of the vertices right? If so, then you can weakly recover the communities, or you can detect that there are communities here. Okay? So basically, if you can do anything better than random, then that's detection. Yes? Yes, so what I care about is as n goes to infinity. Yeah, if n goes to infinity, positive correlation. So bounded away from just a random guess. And so one important comment here is that, which applies to every notion of recovery, is that we won't be able to, so if we have two communities, we won't be able to say that, these guys are from community 1 and these guys are from community 2. We won't be able to distinguish that from the other way around. So that we won't be able to recover the labeling. But that we don't even care really about the labeling. What we care about is the partition that the labeling induces. Okay? So in this notion of recovery and in every other notion of recovery, what we care about, so we're going to maximize over all permutations of labelings. Okay? What we care about is the partition, not the labeling. Is that clear? Okay. So this is the weakest notion of recovery, but you can strengthen this. So partial recovery so if for alpha in 0, 1, we say that an algorithm achieves recovery, what's the term? Yeah, so with accuracy alpha, if it labels an alpha fraction of the vertices correctly. So this is again up to relabeling. And so a particular special case, which is of interest, is when alpha is 1 minus little of 1. So this means a vanishing number as n goes to infinity. And this is also known as weak consistency or almost exact recovery. Now, the strongest form of recovery is exact recovery. So when this happens, if the algorithm labels each vertex correctly. And this is also known as just recovery or strong consistency. Yes, we're assuming here that P and Q is known. But that's a good question. You can think about when they're not known. Yes? You mean if the communities are not balanced? Yeah. Yes, indeed. Yeah, so that's not so interesting, but indeed, yes. Yeah. I guess the interesting case is when alpha is more than what you can do just by random guessing, right? Yeah, that's true. Any other questions? Okay, so in these different with these different notions of recovery, the regime of interest for the magnitude of the probabilities is different. So in particular, this question, weak recovery, is most interesting when the probabilities are at least 1 over n, and exact recovery is most interesting when the edge probabilities are at least log n over n. So let me explain why this is so. So, yeah, let's consider just two communities with no edges in between. So, suppose my Q matrix is just, I have a Q here, and a 0 here, and a 0 here. So this means that this matrix is an Erdős-Rényi random graph with, say, n over 2 vertices. An edge probability Q, and this is also an Erdős-Rényi random graph with edge probability Q. So an Erdős-Rényi random graph is just a graph with n, or here n over 2 vertices, and with the probability of an edge being there between any two vertices, some number, Q here, and this is independent over all possible pairs of vertices. Okay? So now, suppose Q is small. So there's no connection between these two guys. So obviously, if these are connected and these are fully connected, then I will be able to exactly recover these two communities. right? Because there's no edges going in between them. But for this, I need these two graphs to be connected. And the threshold for connectedness in Edder-Shrinian random graphs is log n over n. Okay? So this is why you need at least the edge probabilities to be at least of this order for the problem to be interesting. And it turns out that when they are of this order, then already you see interesting things. And likewise, for the notion of weak recovery, well, if you don't have a giant component in the Edder-Shrinian random graph, so if your graph is just a bunch of small components, here and on the right as well, then, well, if you just give me both of these things in the back together, I won't be able to distinguish, I won't be able to know where I should put this little community, on the left or on the right. Okay, so I need to have a giant component. If I have two giant components, then I can say that, well, I'll put one giant component on the left, the other giant component on the right, and then I'll at least have something better than random. Okay? And the threshold for a giant component in an Edder-Shrinian random graph is 1 over n. So this is why this question is interesting when the probabilities are at least on the order of 1 over n. And in fact, when they are on the order of 1 over n, then interesting things happen. Okay? Okay. So there's lots of work related to all these different notions of recovery. And I do not have the time to, and I do not want to survey everything, but I want to mention some names. So for weak recovery, Dessel et al. In 2011, they conjectured that they conjectured a threshold for when weak recovery is possible or not. And then Massoulier and independently Mossel, Niemann, and Sly in 2014, they proved this in the case of two symmetric communities. And then Abbe and Sandin, last year, they proved this in general for K-symmetric communities. So there are many interesting things going on here. In particular, the information theoretic threshold. So when you can do something information theoretically, if you have infinite algorithmic power, is different when you have at least 5 communities from what you can do reasonably in polynomial time. So there's lots of interesting things going on here, but that's for a different lecture. I won't talk about this. This talk will focus on exact recovery. And here, so this was first studied for two symmetric communities by Abbe, Bandeira, and Hall in 2014 or 14, and also by Mossel, Niemann, and Sly independently. And then last year, Abbe and Sandin so they understood exact recovery for the general stochastic block model. Okay, so this is what I'll talk about in the remaining part of the talk. Any questions? Okay. So our goal is exact recovery, and we'll be in this regime. And in this regime, so let me just put this up here. It's natural to rescale the Q matrix so that now Q is independent of n, and so it has just non-negative entries. Okay, so I'm just taking the scaling out of Q. Okay? Okay. So let me start with a thought experiment. So suppose I tell you the label of every single vertex except one. So there's this vertex V. I don't know its label, but I know that this is the yellow community, and this is the red community, and this is the blue community. And I know all the edges between them. Between all the communities. And importantly, I also know who V is connected to. Okay? So the question is, given all this information, can we recover the label of V? Okay? So this question is important because clearly we have to be able to do this. If we can't do this, then there's no hope of exact recovery. On the other hand, we'll see that if we can do this, then we'll be in good shape. Okay? Okay, so what information can we rely on here? So what do we know about V? So we know how many vertices in the different communities it is connected to. So it is connected to 2 yellows and 3 reds and 3 blues. Okay? Can we use any other information? No, because I've given you the labels of everything else, so the connections here are just determined by these labels, so V has nothing to do with those. Okay? So the only information I have is D of V, which is the degree profile of V. So here, the ith coordinate of this is the number of neighbors of V in community I. Okay? Okay, so what we have to understand is what is the distribution of the degree profile of V and how this depends on its label. Okay, so suppose the label of V is some J. Then what can we say about how many vertices it is connected to in community I? So what's this distribution going to be approximately? So first of all, how many vertices are we going to have in community I? Yeah, so we're going to have about n times pi vertices in community I. And so what will be the distribution of how many? So what's the probability of connection to any given vertex in community I? Yeah, it's going to be, well, qij times log n over n. So this is just, now we've taken the scaling out of the Q. Okay, so this is just the probability of connection to a given vertex in community I. So there are this many vertices approximately in community I. So this will be approximately distributed as a binomial. And so a binomial with these parameters is roughly a Poisson, with mean being the product of these, with mean being the same mean as the binomial, so this will be log n times pi times qij. Okay? And now I'll introduce some shorthand. So capital P will denote the diagonal matrix with the p's, the relative community sizes on the diagonal. And so this is P, the matrix P times the matrix Q, and its jth column. Okay? And so we'll call this the community profile of community J. Okay? So basically, if V comes from community J, then this is the degree profile. If it comes from a different community, then we're always going to have a Poisson, a multivariate Poisson, because, so this, did I mess anything up? Yeah, so this is, what I want to say is that the whole degree profile will be distributed according to a multivariate Poisson. So this is a column vector, okay? Okay, so different communities will have different community profiles, and so the degree profile will have a different Poisson distribution. And what we have to do is, so we've reduced this problem to a Poisson hypothesis testing problem. Okay? Okay. So let me just state this separately. Testing. Okay, so what we have is some random variable h, which takes values in k, so it's one of the k community labels. But we don't observe h, so we do have, so this is a Bayesian hypothesis testing problem because we have a prior on h, which is given by P. So this is the relative sizes of the communities. And what we observe, so there's D, which has distribution. So the conditional distribution of D, condition on H being equal to J, is Poisson with this mean, which scales logarithmically in n, and so it depends on the community profile. And so the goal is to recover H from a realization of D. So that's the degree profile that we see in this thought experiment. Okay? So what is the best thing to do? Yes. So the best thing to do is to look at the maximum a posteriori rule. So this is the map rule. So maybe I'll write this on up here. So you want to pick J that maximizes, well, the conditional, so the probability that you've, so upon seeing D, you want to maximize this probability. Right? Okay. And yeah, so this is, of course, Pj. And so let Pe denote the error probability. So how do you decide between, so which community to pick? Well, one way to do that is to first decide between two communities. You look at communities 1 and 2, and look at which one is more likely, and drop the one that is less likely. And then you say community 2 is more likely, then you compare 2 and 3, and so on. So you have a tournament with k-1 comparisons between the different communities. And basically, it's intuitive that the error probability will be on the same order as the largest error probability that you can make between any two given communities. Okay, so let Pe ij be the error probability that you make when you compare communities I and j. So what will this error probability be? Well, you have to look at all possible realizations, and then you look at the minimum of the two quantities Okay, so this will give you the error you make when you compare communities I and j. Okay? Okay, so now it's an exercise to see that basically, if you want to understand the error probability of the map rule, then you only need to understand these for each pair I and j, at least when k is fixed, and the worst error probability will give you what you're interested in. So in particular, we have the following. So this is an easy exercise that everyone can verify. Okay, so now comes the main result, essentially. Any questions about this? So Abba and Sandon, they characterized this error probability. So for any vectors C1 and C2 any vector k-dimensional vectors such that C1 is not equal to C2, and any P1, P2 positive, we have the following. So if we look at this error probability, so we sum over all x, you look at, so this is shorthand for the probability that a multivariate Poisson with this mean takes on the value x. So this error probability is, maybe I'll write it here. So on the one hand, it's at most n to the minus d plus c1, c2 times 1 over square root log n. And on the other hand, the same thing is at least n to the minus d plus c1, c2 times 1 over log n to the k over 2. Okay, so basically this quantity d plus, which I'll explain to you in a second, is the error exponent in this hypothesis testing problem. Okay, so let me tell you what d plus is. So d plus c1, c2 is the max over t of the sum over I from 1 to k of c1i t times c1i plus 1 minus t times c2i minus c1i to the t c2i to the 1 minus t. Is that visible or is it too high? Maybe I should. Okay, let me write it lower. So it's this somewhat mysterious quantity. And so this has all kinds of connections to various information measures that come up in statistics and information theory, which I'm happy to talk more about offline. I won't have time to talk that much right now, but so because of these connections, Abba Sandin termed this the Chernoff-Hellinger divergence. Because it has various connections to these other divergences. So okay, so this looks a bit mysterious. And that's fine. But perhaps the main point I would like to get through is that this lemma gives an operational meaning to this quantity d plus. Okay, so this has some nice formula, and that's very good because you can compute things. But the main point is to characterize this error exponent, and whatever the error exponent is in this Bayesian-Poisson hypothesis testing problem, that's what is the quantity of interest here. Okay? Okay, so I won't tell you anything about the proof, really. Maybe 2 sentences. So if you consider 2 Poisson distributions like this, and with means mu and lambda, then, well, what you're interested in is this sum under the curve. And it turns out that this point here is essentially mu to the t lambda to the 1 minus t, where t is the maximizer in this thing, in this expression. Okay? So that can give you a hint of why this is important. And you can see that, well, all the other terms don't matter that much. And so this is in 1 dimension, and if you're in k dimensions, then it's a similar intuition. The details I can leave as a challenging exercise for you. But okay, so why is this? What does this tell us? So intuitively, this gives us a necessary condition for exact recovery. So what is this necessary condition? So let me perhaps recap what we did so far. So we started from this thought experiment. So what if we knew all the labels except one? We have to be able to recover the label of this guy if we want to exactly recover the labels of all vertices. Now we reduced this problem to a hypothesis testing problem between multivariate Poisson distributions. And here this lemma characterizes the error exponent of this hypothesis testing problem. So if the error we make here is too large, then we have no chance. So my question is, what does too large mean? Yes, d plus needs to be greater than 1. Because if this is smaller than 1, then essentially you have linearly many of these hypothesis testing problems that you're doing, and so the error probability will not be small. So let me sketch this. So suppose your error probability is n to the epsilon minus 1. So this means that there are two communities, I and j, between which it's hard to test. So for any vertex in community I, you're going to have to do essentially this Poisson hypothesis testing problem. And there are linearly many of these vertices. And they're not independent, but there are many of them which are approximately independent. And so this is the probability with which you'll be correct. And you'll have this many of them. And this is like e to the minus some other constant n to the epsilon. Right? So this is small. And then we're in bad shape. So that's why you need to have d plus between all the community profiles be at least 1. And it turns out that this is exactly the condition. So let me finish by stating the main result of Abbe and Sandin. So suppose Q has positive entries and no two rows equal. And P is also positive entries, and K is just some fixed number. Then exact recovery in the stochastic block model with these parameters and in this logarithmic degree regime is possible if and only if d plus between the community profiles is at least 1. Okay? So basically what I told you explains one direction, and the other direction, so why this is possible if this condition holds, well, that would require another lecture, so I won't tell you about it. But it's very interesting, so I urge you to read more about it in the paper. So my time is up, so this is about all I wanted to say. I'm happy to discuss more things offline. And tomorrow, I'll switch gears into considering networks with geometric structure. Thank you.
Questions, please, get ready.
Yes.
So what happens exactly when G plus is equal to 1?
Then it still works.
Okay.
So yeah, so this is still little o of 1 over n. So yeah, so it's important that there's this 1 over square root of log n here. Yeah. So yeah, maybe one comment is that, well, if d plus is, so this is always little o of 1 over n if this condition holds. So if for every vertex you would just have to do this Poisson hypothesis testing problem, then just by a union bound you would have error that is little o of 1, going to 0 as n goes to infinity. And basically in this regime you can have, the point is that you almost have this thought experiment going for you. Not quite, but you can have a very small fraction of vertices mislabeled, and then you apply this degree profiling step. So you relabel the vertices according to this thought experiment, according to this multivariate hypothesis, this hypothesis testing problem. And then, so you won't be quite there yet, but then you apply this degree profiling again, and then you'll be good. Yeah. So you maximize overall, overall permutations of the labels. Yes, here k is fixed. Yeah, here k is fixed and known, yes. Yeah.
So let's technique here again.